Yes, it's Uncle Jegs. I just clocked that I skipped this final Corona lockdown lesson on concentration. It's so good though. I'm sure you find this lesson useful. We're gonna look at all of these today. From my years of teaching, the one that most students flop on are these three here.
What nonsense is this?
But don't you worry, Uncle Jegs is here to testify. The truth and the honest truth is that these three sections are actually pretty simple if you've been following and applying the science we've been looking at previously. So then, let's chop some science. Here are the retrieval questions for this lesson. You know what to do. The plum pudding model is a sphere of positive charge with negative electrons embedded inside it. This is how J.J. Thomson imagined the atom. The raisins here represent how he imagined electrons were embedded inside the positive sphere. The alpha scattering experiment discovered the nucleus. Man like Ernest Rutherford oversaw that experiment. Finally, Niels Bohr discovered that electrons orbit in fixed energy levels, aka shells. The atomic model before Bohr's model was the Rutherford's model, which had protons in a small dense nucleus and electrons orbiting around it. I'll be going into more detail on the atomic model and atoms in the next few videos, so stay tuned for that. Let's first bag the grade 4 and 6 in the top row, and then we can actually bag the grade 8 from the bottom row as well. Let's imagine that we've got a beaker of sugar. I then add some water to it and we end up with something that looks like this. Pause the video and see if you can link the contents of each beaker to the correct definitions. A is the solute. This is the substance that's being dissolved. B is the solvent. This is the substance that is doing the dissolving. And therefore C is the solution. A good example of a solution is orange squash.
My mum gave me a jam sandwich, packet of crisps, and a box of purple sauce. I've got a turkey sandwich and a Sunny Delight. Sunny Delight, that's something.
A simplified version of this diagram looks like this. What do you think a more concentrated diagram would look like on the particle level? Just have a quick think about this. You should have clocked that you would have more orange particles and less water particles in the same space. In the top box we have 2 particles of orange and 8 particles of water, 10 particles in total. In the bottom we have 5 particles of orange and 5 particles of water in the same space, again 10 particles in total. We have increased the ratio of our orange particles to our water particles. You know what? This 2D image may not give the best representation. The equipments that you use in a lab are all 3D, 3 dimensions. The space inside a 3D object is called the volume. Both of these boxes have the same volume, and the sides on each box is the same length, 1 decimeter. So the height is 1 decimeter, the length is 1 decimeter, and the width is 1 decimeter. What's a decimeter? A decimeter is equal to 10 centimeters. Centi comes from the word for 100 because we have 100 centimeters to make a meter. Deci means 10 because 10 decimeters make a meter. Allow me to geek out just a little bit, yeah? Whenever someone says I'll decimate you, that just semantically means that they'll reduce you by a 10th. The volume of a cuboid is the length times width times the height. This gives us 1 decimeter cubed. The cubed part tells us that we've used 3 dimensions: length, width and height. Let's look at how we now convert from decimeter cubed to centimeters cubed. We see from our ruler that 1 decimeter is 10 centimeters. So the volume in centimeters cubed will be 10 times 10 times 10 centimeters, which gives us 1,000 centimeter cubed. Wait. Don't switch off. Don't switch off yet. Just remember that 1 decimeter is 10 times bigger than a centimeter. 1 times 1 times 1 gives you 1. But 10 times 10 times 10 gives you 1,000. Both of these values measure the same volume, just like 60 seconds and a minute measure the same amount of time. They are both 2 sides of the same coin. This means that to go from a decimeter cubed to a centimeters cubed, you multiply by 1,000. Because to go from 1 to 1,000, we have to times by 1,000. And to get back from centimeters cubed to decimeters cubed, you have to divide by 1,000. Getting from 1,000 to 1, you have to divide by 1,000 to do that. Bringing back our 2 solutions from before, we can be more precise with our definition of concentration. The volume of both of the cubes is the same, but they have different amount of solutes in both of them. This means that concentration is the amount of substance dissolved in a certain volume. Let's imagine that each orange particle represents 1 mole of orange particles. Our volume is 1 decimeters cubed for both cubes. This means that A has a concentration of 2 moles for every 1 decimeter cubed. This gives us a concentration of 2 moles per decimeters cubed. Doing the same for B, we get 5 moles per decimeters cubed. We can clearly see that B has more solutes dissolved in it, and so it is more concentrated. This is the equation that you need to learn. C is concentration, N is moles, and V is volume. Looking at our example here, we can see that moles is in mole, that's the unit. Volume is in decimeters cubed, and so concentration is moles per decimeters cubed, moles over decimeters cubed. You need to be able to rearrange this equation. So concentration is moles over volume, volume is moles over concentration, and moles is concentration times volume. You are meant to be able to work out the grams per decimeters cubed as well, but first, have a go at these 2 questions. For the first one, we have to calculate moles. Our volume is 0.20 decimeters cubed. Our concentration is 1.5 moles per decimeters cubed. Moles is concentration times volume. 1.5 times 0.2, this gives us 0.30 moles. For the second one, we have to work out the concentration, so we are given the volume and we are given the moles. Our volume is in centimeters cubed, so we have to divide the 80 centimeters cubed by 1,000. Concentration is moles over volume. 1.25 moles over 0.08 decimeters cubed gives us 15.63 moles per decimeters cubed. If you got all of that correct,
you smart.
Looking at our success criteria, we see that we have to deal with masses as well as concentration. As I said before, this is where bare students flop, but it really isn't that deep, okay?
Okay.
Before, we define concentration by the moles of a substance dissolved in a specific volume. Each orange here represents 1 mole of orange particle. And just to remind you that a mole is this number of particles.
Do me a favor, please. Get out of here. Get out of here, man.
I know it's starting to look a little bit mad, but if you need to refresh your memory on what moles are, click the card over here to teleport over to that lesson. So yeah, a mole is this number of something. So a mole of hydrogen will have this number of hydrogen particles. A mole of carbon dioxide will have this number of carbon dioxide particles. A mole of iPhones will have this number of iPhones, and so on. Concentration in grams per decimeters cubed just means that the amount of substance is in grams and not moles, but the volume is still in decimeters cubed. That means that if the orange particle represented grams, our concentration would be 2 grams per decimeters cubed. This is what you have to understand. The 2 oranges here are representing 2 different things in each example. To explain this in more detail, it's going to get a little bit sticky, but bear with me. I'll show you side by side what each of these units means in terms of particles. Let's use a molecule of hydrogen for example. Hydrogen travels around as a diatomic molecule, meaning that it has 2 atoms bonded together. Di means 2, just like dioxide means 2 oxygens. So a diatomic particle has 2 atoms. In this example, 1 atom of hydrogen has a relative atomic mass of 1, but since we have 2 hydrogens bonded together in 1 molecule, a molecule of hydrogen has a relative formula mass of 2, 1 from each atom of hydrogen. Remember from our previous video that for GCSE, a mole is the relative atomic or relative formula mass of a substance in grams, and a mole is equal to this number of particles. In the example on the left hand side, we have 2 moles of hydrogen in each decimeter cubed. What that means is that since 1 mole is this number of particles, 6.02 times 10 to the 23, we must have double that amount in that space. Double because we have 2 moles. If it was 3 moles per decimeters cubed, we'll have triple. If it was 4 moles per decimeters cubed, it will be quadruple, etc. So 2 moles of a particle is 1.2 times 10 to the 24 particles. Now, 4 grams per decimeters cubed. A mole is the relative atomic or relative formula mass in grams, and it is equal to this number of particles. The relative formula mass of hydrogen molecule is 2. So 2 grams of hydrogen will have exactly 1 mole of hydrogen particles inside it. So if we had 2 grams of hydrogen dissolved in 1 decimeters cubed, we essentially have 1 mole of hydrogen dissolved there. Because the relative formula mass of the molecule of hydrogen is 2, and our definition of a mole is the relative formula mass in grams. Obviously, if we use a different substance, it will have a different relative formula mass, and so the moles will be different, even if we're using the same amount of mass. Helium, for example, travels around as a single atom and has a relative atomic mass of 4. That means that 4 grams of helium will have this number of particles, because that will be 1 mole of helium. Remember that a mole is the relative atomic or formula mass in grams. The left hand side will stay the same, because 2 moles of helium is double the number that we see here, which is gonna be 1.2 times 10 to the 24. However, 2 grams of helium is half a mole of helium because a mole of helium is 4 grams. That means if we have 2 grams of helium, we have half this number of particles, which gives us 3.01 times 10 to the 23 particles. I promise you, it really isn't that deep. It just looks confusing because your brain has to get used to thinking like this. Use the timestamps below to jump to where you started getting confused and just try again. To be fair, you can just learn how to do the calculations without really understanding what's going on. I don't recommend you doing that, but it's better than nothing. Look at this worked example. It is asking us to work out the concentration in grams per decimeters cubed. We have been given the grams and the volume. Concentration is mass over volume. So 10 grams over 2 decimeters cubed, that gives us 5 grams per decimeters cubed. That's light work, isn't it? This next one's a little bit trickier. We have again to work out concentration in grams per decimeters cubed. We have the mass and we have the volume like before, but we have to convert our volume from centimeters cubed to decimeters cubed. Hopefully you remember that that means we have to divide by 1000, so our volume is now 0.25 decimeters cubed. 3.8 over 0.25 gives us 15.2 grams per decimeters cubed. Now have a go at these quick check questions. Pause and then come back for the answers. In both questions, we have to work out the grams in decimeters cubed, and we've been given the grams and the volume. The first one is simple, mass over volume. That will give you 5 grams per decimeters cubed. For the second one, remember that our volume should be in decimeters cubed, so you have to divide by 1000 again. So 1500 divided by 1000 gives us 1.5 decimeters cubed. Then mass over volume, that gives us 17 grams per decimeters cubed. We're now one step away from completing all of the success criteria for this lesson. This question here is asking us to work out the mass of hydrochloric acid that was dissolved in 0.20 decimeters cubed to give a concentration of 1.5 moles per decimeters cubed. We have the volume and we have the concentration. We have to work out the relative formula mass of hydrochloric acid, 36.5. The actual unit for your molar mass, for your relative formula mass or relative atomic mass, is grams per mole. I'll add it here for those of you that are working for grade 8 and grade 9 because it will make sense later on. Moles is concentration times volume, CNV, which is 1.5 moles per decimeters cubed times 0.2 decimeters cubed. This gives us 0.3 moles. And to get from moles to mass, we need the molar mass, aka the relative formula mass in this case. Mass is moles times molar mass. That gives us 0.3 times 36.5 grams per mole. And the final answer then, our mass is 10.95 grams. Please memorize these two equations, okay? Here's another example.
Another one.
Have a go at answering this. Again, we have the volume and we have the concentration, so we can work out the moles. The relative formula mass of sodium hydroxide is 40 grams per mole. 0.4 moles per decimeters cubed times 4.5 decimeters cubed gives us 1.8 moles. So the mass is 1.8 moles times 40 grams per mole, which gives us 72 grams. Okay, this last example is probably the hardest of these type of questions that you'll get.
Just prepare to go to hell.
I won't give you any hints here. Try and complete this question. There are two things that could have tripped you up here. First, you need to make sure that you multiply your oxygen and hydrogen by 2 when working out your relative formula mass, because we've got this bracket and a 2 on the right hand side of it. Remember, that means that everything within there, we have 2 lots of it, so you times the oxygen and the hydrogen by 2. This should give you a formula mass of 74 grams per mole. The second thing that could have tripped you up is converting your centimeters cubed to decimeters cubed. That means that our moles is 0.87 moles per decimeters cubed times 1.25 decimeters cubed to give us 1.0875 moles. To get this moles to mass, we have to multiply moles by our molar mass. So our moles, which was 1.0875 moles, times our molar mass, which was 74 grams per mole, gives us 80.46 grams.
Hey! Wow! Wow! Let me go home.
And there we go. Lesson is done.
Fatality.
Check the timestamps below to skip to exactly what you need if you're confused with any bits of that, and I'll catch you guys in a bit.